In this video, we'll introduce Davenport-Schinzel sequences. Consider a set S of n symbols. We'll look at strings created by these symbols. A string is a sequence where we repeatedly put these symbols one after another. We say a string or a sequence is valid if there are no immediately repeating characters one after another. For example, in the first string up here, we have two repeating C's that are immediately adjacent, and also two repeating D's, and two repeating B's. This makes this first case invalid sequence, whereas the second example is a valid sequence. Even though there are many repetitions of A, there are always at least one other character between each repetition. Finally, we need to look at the concept of matching. Consider a sequence sigma and a pattern P. The pattern is another sequence or a string over another alphabet. In this example, the pattern is over alphabet X, Y, and Z. We say a sequence matches a pattern if we could relabel the symbols in this pattern P such that the resulting relabeled pattern appears as a substring of the sequence sigma. For example, in this case, we could relabel X as A, Y as C, and Z as D. If we do this relabeling, the pattern would turn into pattern ACD, ACDCA, and we could find this pattern as a subset or a subsequence of this sequence, as you can see in the picture. This means this pattern, this first sequence matches this pattern denoted here over a different alphabet. And at the end, we define a Davenport-Schinzel sequence of order S as a valid sequence that avoids a pattern AB, AB, etc., where the length of this pattern is S plus 2. And we denote the maximum possible length of such a Davenport-Schinzel sequence of order S with ds subscript S of n. Now we'll want to look at what is the value of this maximum for different values of S. First, we look at the easy case, ds1, which means a sequence that avoids ABA. Let's look at some easy cases. If you have only one character or one symbol, there's only obviously one possible sequence, A. If you have two characters or two symbols, A and B, this is as far as we could go. First we start with A, we cannot repeat A, so it has to be B. And now we cannot repeat B, and we cannot repeat A because then we would have ABA. Let's look at sequence of size 3. We have to start with some symbol, let's call it A. We cannot repeat A, so it has to be B. We could not repeat B because then we'll have two immediately identical characters. We cannot do A because then we'll have ABA, so it has to be C, some other character, the last symbol. And after this, again, we're stuck. We cannot repeat A because we'll have ABA. We cannot repeat B because we'll have BCB, which is a pattern that matches ABA. And we cannot repeat C. So this is as far we could go. And in fact, as you can see, the maximum size of a Davenport-Schinzel sequence of order 1 is n because we cannot repeat any symbol more than once. Let's look at order 2 sequences. These are the sequences that avoid AB, AB. Again, if you have only one symbol, it's easy. If you have two symbols, we have to start with some character. It has to be some character, some symbol, we call it A. We cannot repeat A, so it has to be B. And now we can put one more A because we have ABA, and now we're stuck. We cannot repeat A again, and we cannot repeat B again. So this is the maximum for n equals 2. For n equals 3, again, we have to go ABA. Oh, we have two cases, in fact. Has to be start with some character, we call it A, has to continue with some other character, we call it B, and now we have two cases. Either we repeat A again, or we use a different character C. If we repeat A, we cannot repeat B because we have ABA, so it has to be C. And we cannot repeat C, we cannot repeat B again because we have A, B, A, B. So has to be A basically. If we go with ABC, we cannot repeat C, we cannot repeat B. We could have B. We cannot have A because then we're stuck. So we have to go with B, which will leave us only choice of A for the end. So with some case analysis, it's easy to see that for n equals 3, the maximum size can be at most 5. And now we prove that a Davenport-Schinzel sequence of order 2 can be at most 2n minus 1 size in length. The proof goes as follows. We claim that there has to be at least one symbol that appears at most once. Imagine this is not true. Imagine we have a sequence where every symbol appears at least twice. Let's look at two copies of some symbol where the gap between them is close as possible. Let's call such a symbol A. Since we know this is a valid sequence, there has to be at least one other character between these two copies of A. Let's call that character B. Since we assumed every symbol appears at least twice, there should be one more copy of B, at least in the sequence. The copy of B cannot be here because then we'll have BA, BA, which is a symbol which matches the pattern ABA, ABAB. We cannot also have B here because then we'll have ABAB. Thus, the only choice for the other copy of B is that it has to be between these two A's. But that's a contradiction because we assume these two A's were the closest two copies of any symbol in the string. And now we find another copy, two B's that are even closer. So there is a symbol that appears exactly once. Let's call that symbol A. We have two cases. Either the preceding and succeeding symbols after A are different. So for example, some B and some C. In this case, we could delete A, or they are the same. In the second case, we could delete A, but now we also need to delete B, because by deleting A, we get an invalid sequence. But notice that by deleting B, we'll never get an invalid sequence, because the character following this B cannot be B, and the character before this B cannot be B. So this means by deleting AB, we get to a valid sequence. Starting with n symbols, each time we can delete one symbol. If we repeat this n minus 1 times, we'll end up with a string that has only one symbol, that is only made of one symbol. And we know that the maximum length of a sequence with one symbol is 1. So with n minus 1 deletions, we'll be deleting at most 2 times n minus 1 characters, which will take us to a string of size 1, which means the maximum length is at most 2n minus 1 plus 1, which is 2n minus 1. And now finally we look at a sequence of order 3. Such sequences avoid repetitions or avoid patterns of AB, AB, A. We claim that we could bound the maximum size of such a sequence with n log n. Let f of n be the maximum possible length that we could obtain for such a sequence. This of course means that we have a string with length f of n given n symbols. Since the length of the string is f of n, there has to be one symbol, which we denote with A, that appears at most f of n over n times. Because if this is not true, if every symbol appears more than f of n over n times, since we have n symbols, it follows that the length of this sequence is bigger than f of n. So this is true, and if we have a symbol that appears less than this many times. Let's look at the repetitions of this symbol. We have A appearing at some positions in this string. The claim is that if we look at the inner occurrences of A, so not the first occurrence and not the last occurrence, somewhere in between, that the two characters immediately before and immediately after this copy of A cannot be the same. Imagine such an A, which is not the first A and it's also not the last A, where these two characters are the same. Then we will find a subsequence that matches our pattern. We will have A, B, and A. Thus, it follows that these two characters cannot be the same. And I would like to delete all occurrences of A. From what we argued, deleting an interior A is for free. Since these two are not the same, we could just delete A safely. However, the first occurrence of A and the last occurrence of A might cause us to delete one extra character. In this case, we might have to delete two extra characters. By deleting A, we get a sequence that has one less symbol, and thus its size is bounded by f of n minus 1. However, we have deleted at most f of n over n plus 2 strings, which means the size of the remaining string is f of n minus f of n over n minus 2. We can at most delete this plus this many characters from this sequence. If you put these two inequalities next to each other, it follows that this value should be smaller than this value. And now we need to find this recursion. By some simple manipulation, we get to this recursion, which we know how to solve because we can just relabel this function as a g function, which gets us to this. And thus g of n is less than or equal to g of n minus 1 plus 2 over n, and thus g of n is bounded by the harmonic series. So g of n is at most log n. And since g of n is f of n over n, it follows that f of n is at most n log n. Using these sequences, we can bound the lower envelope of a set of functions very easily. Let's look at a set of lines. The claim is that the complexity is linear because this is a Davenport-Schinzel sequence of order 1. A set of right rays again have linear complexity because this is a Davenport-Schinzel sequence of order 2, and in fact the complexity is 2 times n minus 1, which is better than the n log n upper bound that we could prove in the previous video. And finally, for a set of line segments, it can be seen that they form a Davenport-Schinzel sequence of order 3, and thus the complexity is bounded by n log n. In fact, it is possible to show even a better bound of n alpha n, where alpha is the inverse Ackermann function. We will not discuss the exact definition of inverse Ackermann function. You can find them in various other resources. But it suffices to say that the inverse Ackermann function is a very slowly growing function that is much smaller than log n. And also, this bound is tight, and in fact, we can create a set of line segments that achieve this bound. And this concludes our discussion of Davenport-Schinzel sequences.